So we heard from the government and the public's point of view this morning. Now we're going to hear from the pipeline operator's point of view, and we're going to have a panel discussion afterwards. Thank you. Max Kiba is going to introduce our operators that will be on the panel this afternoon.
Hi, everyone. And I did want to thank the operators that were able to come here and help us. I will say it was a little difficult getting some of you operators to help us out on this one. I think it was a combination of just bad travel and what I understand, a lot of you are here too, trying to figure out where are we going on this. So I do appreciate the operators that were able to step in and help us out. First up, we have Jason Smith, Director of Asset Integrity from Magellan Midstream. Jason's been with Magellan for over 14 years now, and he has a Bachelor of Science in Civil Engineering from the University of Oklahoma. So, Jason.
All right, thank you, Max. Good afternoon, everyone. Appreciate the opportunity to be here with you today. So like Max said, my name is Jason Smith. I'm the Director of Asset Integrity at Magellan Midstream Partners. We are a refined products and crude pipeline and storage transportation company, principally located in the central U.S. Now, there's a lot of different ways I think we could talk about IBP in detail, but for the purposes of my discussion here, we're really going to focus on what Magellan's current MOP verification program is, and not only our verification, but how we established our MOPs. And then we're going to kind of shift into how we supplement our MOP determination and verification process with our IMP, and what activities and considerations that should be a part of your MOP program and where you're comfortable with operating. So we'll talk about that a little bit too. And then finally, we'll wrap up with the Longhorn Pipeline Project. And this was a project where we had an established MOP, but we worked through conducting some additional verification steps to validate that the MOP we had was accurate. So MOP verification. So if you're a liquid operator in the room, you know MOP starts with 49, 195, 406. So for Magellan, years ago when we started consolidating our MOPs, it really started with our as-built documentation. And so what we did is we started going through all of our records and pulling out the unique vintages of pipe that we had. So by vintage, I mean each combination of wall thickness, grade, seam type, manufacturer, and really documenting that in a concise form. All of our MOPs, we started calculating on one form. So we had a quick, concise record of all the pipe that was a part of that pipeline system. And then, of course, we supplemented that with components. Where are they at, where are they rated for, what type of component is. And so all that was rolled up into what ultimately became our compliance subpart E pressure test. For us in Magellan, the pressure test is significant in terms of establishing that MOP, because that's the one verification that you have that really touches every foot of that pipe, as opposed to maybe some tighter statistically sampling that you do. So MOP is really the driver for, or pardon me, pressure test is really the driver for how we establish MOP. I think it's really critical when you're talking about now you've calculated this MOP is that documentation, because it rolls out into so many other important factors within your programs. It's not just where you set your MOP, but it's also your operating pressures as far as discharge, shutdown, your assumptions that go into your surge analysis, your relief set points, and even your MOP alarms that you're using in your SCADA system, so you can ensure that you're operating below the allowable limits. So we want to be able to step back from, let's say you go to that alarm that's in your SCADA system, and you want to know how you derived it, is you want to be able to go back and pull that documentation very quickly and have the information that supports that. And then I think the next step is recognizing how important MOPs are, is to routinely go through and verify those. So for us, at least every 5 years, but oftentimes more often than that, is we'll go back through and completely re-verify our MOP. So that means going back through all those pipe specifications and validating that the records that are in our MOP calculation and the records that are in our as-built still match. it's physically going and putting our hands on the hydrostatic test record and going through every one of the pages and validating that all the documentation that's required under Subpart E is there. And then it's also going through the discharge calculations and the surge analysis and your MOP alarms that are in your SCADA system, and we completely revalidate all that. And you may ask, well, don't you have a change management program to ensure that your records don't change and that you keep track of it? We do. We have a very mature management and change program, but it's the recognition that there's still human intervention involved, even if it's the individuals who's inputting pipe data into whatever mechanism you use to record your data. And so it's a layer of protection. It's a recognition that MOPs are important and that factors could potentially change over time, and so we go back through every one of our MOPs, like I said, at least every 5 years. Now, integrity management, and I do think integrity management is an important component of MOP validation, and understand that it may look like a black box, but I think you also have to recognize that each pipeline, each vintage, each threat, they all have specific attributes, and you need to be somewhat flexible in integrating data. And I've listed a lot of points here that you might consider, but how do you operate that line? What percent SMICE? Is it legacy pipe? Is it modern pipe? And there's a lot of different things you could do. And you may choose to do a spike test, and that's certainly valid for certain threats. There's also a lot of questions, I think, that we talked about earlier on spike tests that we still do have to address and understand. Another thing you may do is you may adjust your MOP, or you may adjust your discharge pressure. I think one example that you could do that could impact the threat of a release at a pressure lower in your MOP is look at your relief set points. Do you have them set at, if you have an MOP, do you have them set at 1400, or do you have them set at 600, recognizing that you normally operate at 500? So how can you influence the overall risk profile of that pipeline? There's a lot of different decisions that come out of that integrity management program that takes a lot of integration of good quality data. And it does still come back to data, because you're only as good as the data you have. So you want to be able to integrate that and have that accessible and make the decisions that you want to execute on your pipeline after that. So let's talk about our Longhorn Pipeline project. This was a 500-mile crude project that was going from Crane, Texas to Houston, Texas. It is a 1950s vintage asset, so given that, as you might imagine, not every MTR was readily accessible. But what we did have is really good as-built documentation on it, and we also had a fairly recent pressure test. It was a 1.25 MOP, 8-hour continuous pressure test. Now this pipeline, it had a very specific permit approval process that went along with it, and we had very good, productive, collaborative efforts with PHMSA navigating what that approval process was going to be. And so, fortunately for us, the pipeline was already displaced as part of the project, but what we did is we went through all the different vintages of the pipe, and where we didn't have MTRs to support the as-built record is we went and did a series of cutouts. And so those cutouts we sent in for destructive testing. And so we supplemented the destructive testing by doing some non-destructive testing on those exact same cutouts. And the objective of doing the non-destructive testing is over time to continue to build a statistical sample. You obviously start with a very small statistical sample as far as cutouts go, and you're building towards that to continue to validate what your pressure test has told you. I mean, ultimately, the MOP was established by the pressure test, but we want to make sure that the non-destructive testing or the destructive testing validated that. And the end result is that it was. The non-destructive testing and the destructive testing results were very close to each other, probably about 10% difference when you're looking at yield strength and toughness. And you know, what that allowed us to do is as we set up long-term additional non-destructive testing that we did, is we had high confidence that it was going to be fairly accurate. So part of the permit approval process was committing to continue to do non-destructive testing on 50% of our ILI features that we do. And so as we've progressed, it's been a couple years, I think now, all the testing that we've done has continued to validate that our as-built records were correct. and our MOP and the assumptions that went into our MOP were valid. So just quick wrap up, for us, the hydro test is still where we start in our MOP determination. It's a verification that covers the entire asset. And then I think a part of that is the second step is that continuous review you do of your as-built records. Go back through those, look for data changes that may have happened, validate if you've had a management change that's occurred between the last time you validated your MOP. Make sure that that's been appropriately accounted for. And then I think where a lot of us operators are today is continue to research the MTR records, and I think that's one of the things that if you're looking for maybe what you don't know, part of digging into those records that you have and finding those MTRs is where we're at. But there's also another opportunity too that I think is good to take advantage of is whether you have MTRs or not, is take advantage of the cutouts you're already doing. If you're doing a relocation or a tie-in or some project where you're going to be cutting out pipe, it's a great opportunity to continue to build your statistical sampling of that specific asset and validate the records that you already have. And then you can continue to supplement your MOP verification by your IMP. Look at where you're operating at, look at how you set your MOP. I'd say even take that further to relief set points, your surge analysis assumptions, and determine if you want to operate lower. I mean, I think there's a lot of different ways you can take integrity management. Like I said, you may decide that spike test is the best option. It really just depends on the asset, I think. And finally, I think what we saw with the Longhorn project is we had good as-built documentation and we had a pressure test, and we supplemented that with some additional sampling that really validated that the process that we had gone through as far as establishing MOP and verifying MOP were true. So that's all I really had. Any questions? Okay, thanks.
Thank you, Jason. Next up, we have Philip DePriest. Philip joined Marathon Pipeline Company in 1985 after graduating from The Ohio University. I heard you have to say The Ohio University or something like that. Oh, it's Ohio Northern. It's The Ohio Northern University with a Bachelor of Science degree in Mechanical Engineering. He served in a variety of projects, including project manager for grassroots refined product breakout storage, regional manager over multi-area field operations staff, product quality manager for Marathon Petroleum Corporation. He is currently manager of Integrity, Damage Prevention, and Risk Department, where he has responsibility for integrity, management of mainline prevention, and risk management processes. He's also a member of API's Operations and Technical Group and vice chairman of PRCI. So, Philip, please.
Thanks, Max. Sorry I'm a bit tardy here. We had a little trouble kicking out the breakfast crowd this morning for lunch, so just made it back just in time. Appreciate the opportunity to come to the forum and provide comments on the proposed IVP on behalf of the hazardous liquid pipeline industry and Marathon Pipeline LLC. Having these types of forums really does benefit us to work collaboratively and to figure out solutions to the problems that we have in our industry and gain effective solutions going forward. For those of you that are not familiar with Marathon Pipeline, I'll just quickly show you our footprint here. We operate over 6,000 miles of pipeline in 14 states, from the Gulf Coast to the Midwest, safely moving nearly 3 million barrels or approximately 120 million gallons every day. Before I go into making some comments specifically on the IVP, I wanted to first take a few minutes and quickly run through what are the stated primary high-level goals from key stakeholders. So first from PHMSA, I found their mission and vision statement on the website, and just reading through those statements. Our mission is to protect people and the environment from the risks of hazardous materials transportation, and our vision is that no harm results from hazardous material transportation. Pretty hard to take exception to that. I think that's well stated. Now let's take a look at the shared pipeline safety principles that are documented in the 2015 API AOPL Annual Liquids Pipeline Safety Performance Report and Strategic Plan. Zero incidents. We've heard that several times today, and it stands prominently at the top. Pipeline operators do have the mindset that every incident is preventable, and we work very hard each and every day to try to achieve that. Organization-wide commitment to safety. It's not just the leaders at the top of our organizations. It's a culture that needs to permeate all the way down to the frontline worker, and where we have a continuous improvement mindset that resonates throughout the organization. Learning from experience. Operators, of course, learn from their own experiences, but we actively share lessons learned amongst ourselves, and we have a variety of forums that we have in place to accomplish that. It's you know, as we continue to drive our incidents lower and lower, we need to look to the pool of operators to see what's learning, why are these incidents causing, get to the root cause. That's where we can really learn and benefit from our sharing. Systems for success. Operators in partnership with PHMSA and many other stakeholders have developed a pipeline safety management system recommended practice document, and operators are now looking forward to the process of implementing those systems or strengthening ones that they already have in place. It's a structured approach to continuous improvement through repetitive plan, do, check, adjust cycles. Employ technology. Operators continue to pursue new ways to maximize safety with effective technology. And then finally, communicate with stakeholders, just like we're doing today, getting out and having interaction and sharing our perspective and learning from others. And then I wanted to just show you Marathon, excuse me, Marathon Pipeline's guiding principles. And again, at the top, leading safety performance, the safety of the public, our employees, and contractors is our top priority. Down to the bottom right, operational excellence is the driving force toward flawless performance. And another one, engaged employees. Everyone is fully engaged in achieving our vision. So I just wanted to go through those to reinforce the point that there is clear alignment of our objectives, and that PHMSA, the hazardous liquid pipeline industry, Marathon Pipeline right there with it, many of my colleagues in the audience, I'm sure, would stand tall with this as well. We have very similar aspirations, but I think what we're here to talk about is how does the proposed IVP effectively help achieve them. So with that, I'll provide some comments on various elements of the proposed IVP. Starting with spike pressure testing. So what is it? Spike pressure testing is an integrity assessment method to identify and eliminate a very particular set of critical defects, those that might be growing through pressure cyclic fatigue, okay? It's not a tool for establishing or verifying maximum operating pressure. We already have very clear guidance in the code on how to establish or verify MOP. Operators design spike tests to, with an incrementally higher pressure above their intended MOP so they have a fatigue life to work within. And, you know, it's very dependent upon the operating conditions of a pipeline. If there are many, many pressure cycles, an operator would choose a higher spike test pressure to have a longer fatigue life. On the other hand, if the line was operating with very small or a few cycles, the pressure wouldn't need to be set as high. So the dependency of testing pressure at a fixed level is not really relevant. It's more thoughtful as to what fatigue life that you are targeting. There are also consequences with spike testing. Damage. Hydro tests cause damage. It's a destructive test, and you know we're failing pieces of pipe, and we are also causing what might otherwise be stable anomalies to grow and then potentially start fatiguing. We've observed through successive pressure testing, looking at test failures under the microscope, where you can see tearing occurring during successive hydro tests, tearing, a little bit of fatiguing, tearing, a little bit of fatiguing, and what we're ultimately causing are these anomalies to fail sooner than what they would otherwise. So we've got to consider that as part of the equation here, is that this test has its place, but it also has some detriment, and that we need to weigh that. Other limitations include the fact that this assessment methodology doesn't provide insight into what other anomalies might be on that particular pipeline. It will cause anomalies that have grown to a critical size to fail during the test, but there will be others that survive the test that an operator will not be able to know through this particular means. So that's another limitation. And then there's really no technically defendable reason to pursue a spike test for most lines that are operating at low stress levels. If lines aren't, if we don't have anomalies that are fatiguing, or we have fatigue lives that are dozens, if not hundreds of years into the future, there's really no need to apply this type of assessment method to those. It has also been suggested that operators design spike tests to pressures to 90, 100, or even a higher percentage of the specified minimum yield strength of the pipe. It's just not practical or technically sound to spike each pipe wall thickness grade combination that might exist in a particular length of pipe. And I'd like to try to illustrate that on this MOP profile. Across the bottom is miles of pipe. The black line that you see there is representative of the elevation profile, so the y-axis is elevation in feet. And then the blue or aqua line you see there across the top represents 100% specified minimum yield strength. And the spikes that you see there are representative of heavier wall pipes, that may have been installed at road crossings or river crossings, or maybe replacement sections over periods of time. It could be a block valve that has a pressure rating that's different than some of the pipes. So to accomplish a test based on SMIEs, test segments would have to be broken up to accommodate each one of these spikes. And this is just an example. And there's a number of systems that are built maybe 10, 20-mile segments, and you would really have to take a lot of effort to bust up a pipe system to accommodate a test like this. So let me go from there to engineering critical assessment. As we've heard this morning, there really is some uncertainty remaining on what PHMSA intends here, and we hope to have some continued dialogue to understand what's on their minds and how we can add to that. Well, I think it may have also been mentioned that PRCI has a project underway to develop guidance in this area, so there is some clarity coming from an industry perspective on what this needs to be and something that operators can draw upon for guidance. I guess I would also contend that engineering analyses or assessments are already an integral part of our integrity management protocols. It's an engineering assessment that's not done one time. It's done each and every time we conduct an integrity assessment. There's a whole bunch of engineering science that goes into the entire process, and this wheel that I have on the slide here graphically depicts typical steps through that process where an operator would perform a threat assessment. What do I know about my pipe? What don't I know? I select an assessment methodology to best identify those particular threats. I perform the assessment. I characterize the anomalies. I repair the defects. I evaluate post-assessment what I've learned, what I might need to change. I determine what my fitness for service is, and then I start again. And in each one of those processes, you see a little plan, do, check, adjust wheel. And each time we perform an assessment, we learn. And we take that learning and we apply it and we improve our processes, and we help try to find all the many blind spots that might be out there and get better with each time. The other point here is that these analyses that we perform, they're very unique to a given pipeline system. It's not something that you can broadly apply an algorithm and fit all of the needs for a given pipeline system. It's very custom, very tailor fit. So let's talk a little bit about material documentation. Quite frankly, the suggested approach will not be practical in most cases and provide only limited value. You see I've got a needle here in a straw pile. Looking for the needle through digging and testing is not really likely to bear fruit. And then even the most complete record keeping might not reveal vulnerabilities and could provide a false sense of security. It's, one might think that they have a complete record system, but that's not to say that somewhere along the line something didn't go right, and the record just doesn't reflect that. So the area of focus, I think, really needs to be placed on technology solutions. Where we have gaps or weaknesses in this area, we really need to be figuring out what the technical R&D that we can perform to fill in those gaps. And in fact, there are a number of projects that are underway to help in that regard. And certainly a successful sub-party hydro test, if there's a documented, thoroughly completed sub-party hydro test, that should be an acceptable alternative to going through this exercise. So I guess to kind of provide some closing thoughts here, we really need to keep our technical experts focused on the problems that are plaguing us the most here. We need to have them focused on mitigating the highest risks. And if we divert those resources to things that are more administrative, it could cause us to take the eye off the ball and introduce vulnerabilities. Also, as I mentioned, integrity management it's a complex undertaking. There's a fair amount of high-intense engineering that is done on each and every segment, and we can't reduce that to a one-size-fits-all algorithm and apply that and expect that to work each and every time effectively. Risk mitigation, which is really what we're trying to accomplish, needs to be laser-focused on a system-by-system basis. And then finally, where we might have global technical weaknesses within integrity management, let's work together, find what those weaknesses are, and then tailor-fit solutions, not in a shotgun manner trying to hit everything kind of loosely, but let's laser focus our energy, find where we have weaknesses, collaborate together, and shoot towards the objectives that we all aspire for. Thank you. Questions?
Thanks, Philip. Next up is Jake. Questions already? You're done? Thanks, Jake. No. I'll let Jake expand on his background, but I know he's been around certainly in my 8 years being with the industry and a number of operators. I think you've helped us in some of our prior workshops, so definitely active in PRCI. So, yeah, here's Jake.
So we've heard a lot today about what's in the black box. What is ECA? What are the guidelines? What are we getting ourselves into? Speaking for a number of operators I've talked to, when we saw the first IVP charts, we asked ourselves the same question. Came together under PRCI and said, PHMSA has given us an opportunity to get ahead of this and offer some technical suggestions or some guidelines or to start putting a framework around this ECA process. So what I'd like to do today is kind of share with you what the PRCI project's about, where we're headed with developing these guidelines, and try to walk through some of the things that we think are important in terms of IVP and ECA, and perhaps show an example or two of how we think this might play out. So where does ECA fit in the IVP? You guys have all seen the flow chart several times today. Both the gas and the hazardous liquids IVP flow charts allow for an engineering critical assessment to be done when test records and material records are less than perfect. But as we've all asked today, what exactly do we mean? A couple drivers for the ECA development, particularly from the PRCI standpoint. The industry recognizes that there's a lot of line segments out there, both in the gas and liquid industry, that it's going to be very difficult to meet IVP requirements for test records and for material documentation. A lot of these pipelines predate any kind of regulatory code, so whether they were built to ASME standards or company standards, they may have some of these records, but not all. We also recognize that technology is evolving pretty rapidly, particularly in the ditch evaluation techniques. ILI technology is also evolving. And we want to try to leverage that in our ECA guidelines. So what exactly is an ECA, and what is it for? The purpose is to determine if a piece of equipment or structure is sound enough to meet the service requirements for what it is intended. This is a pretty general definition. I believe it comes from ASME. 1104, API 1104 also has a definition similar, is an analysis based on fracture mechanics principles or whether or not a given flaw is safe from brittle fracture, fatigue, creep, or plastic collapse under specific loading conditions. Now, as you all know, 1104 is a standard for girth welding. So in this definition, the context is girth weld flaws. And of course, the IVP flowcharts also offer some description of what they mean. The project's goal is to develop these guidelines. We want them to be flexible and practical. They need to be based on integrity principles and integrity best practices. We intend for them to be suitable for both hazardous liquids and natural gas. The integrity science is the same. We do look at this as a one-time exercise to support MOP, MAOP. And when we reflect on, or when I reflect on some of the comments I heard this morning about the reoccurring nature of MOP justification, we see and we're concerned about a blurring of the lines between integrity verification process and integrity management program. A lot of the things that were talked about this morning about fatigue life calculation and reassessment interval determination and fitness for purpose, those are that's blocking and tackling of integrity management. The existing integrity management programs are built around that. So we got to figure out, and it's important to us as an industry, to understand what's the difference. If what we really are saying is integrity management regulations aren't adequate, then let's say that. Let's come out and say we need to change integrity management program regulations. Let's not call it something different and confuse the industry. And Steve mentioned this morning, that he's heard that there's been an effort to kind of change the name of the ECA process. And the PRC, I don't know if he heard it from the PRCI group, but we kind of looked at ECA and we said, you know, there's a name, ECA is used in ASME for this reason, and 1104 has a definition, and we're talking about something different. Maybe we ought to change that definition and so we can have clarity on what we're trying to accomplish. And now at least speaking for myself, not the whole PRCI team, I wonder if, rather than ECA, if we shouldn't have tried to change IVP to some sort of MOP verification process, just so we're clear what we believe to be a one-time exercise that is based on integrity management science, and keep that clear and distinct from integrity management programs. And I'll talk a little bit more of that as we go. But it's kind of a revelation for me this morning. I want to get out there for discussion because it's just that important. We know it's the right thing to do, but it's important that we're clear on what the requirements are. So as Phil alluded to, we can focus our experts where they need to be, and we can properly respond to these requirements. The pipeline industry believes that we have a substantial volume of knowledge, experience that we can use from our integrity management programs to an ECA process. They're closely linked. And we feel like, as the practitioners of integrity management, we're the best ones to try to come up with a guideline or a framework of guidelines. Project has 23 participants. We have hazardous liquid operators. We've got some natural gas operators. We've also got some industry experts on the team. It's not just operators. And we welcome Steve's comments from this morning. You know, they're very interested in what this project's going to come up with. We'd love their involvement. We'd love their feedback as we go. Is this, you know, can we fully understand and hit the mark on what they want for IVP? We plan on leveraging several other PRCI projects. There's a project right now underway to develop guidelines for when to do hydrostatic testing and to what level, based on appropriate need. There's also several projects that have to do with the in-ditch materials characterization, and a project on how do we connect the dots of all the in-ditch work with ILI data. And we think, not to jump ahead of something I want to cover later, but we think that's an opportunity for this PRCI project, is to put these things together, and what does that mean in the context of material documentation. I mentioned this earlier, what's in a name, ECA versus MVA. Right now, the project team, we like the phrase MVA, MOP, MAOP verification analysis, because it's what we expected the focus to be. Is we have less than perfect test records. We have less than perfect material documentation. What can we do to make up that gap and show that our pipelines can support these operating pressures? We offer up a definition of ECA or MVA as an engineering critical analysis based on integrity management principles, whether or not a pipeline has sufficient safety margins under specified loading conditions. So we think by leveraging integrity management principles, we can make up for not having a pressure test calibration certificate, or maybe not even having a test station location. There's things that we can do from an integrity standpoint to make an equivalent safety margin to what that piece of paper would give us. And I'll share an example of that later. Rough outline of our approach. We're calling them parameters in this presentation. What we mean by that is all the record and material record documentation requirements. Each of one of those is a parameter in our language that we want to address somehow. We want to take a look at each one of those. What are the relevancy for safety and integrity? More on that in a minute. What data is out there that we can use that's applicable to each one of these parameters? What existing technologies out there that we can also use? What existing processes can be used? What kind of gaps are out there for technology and process? And then finally, we want to come up with a matrix or a table that says, hey, if this is the thing that you're missing, here's all your options to demonstrate that the pipe can be safe, just as safe. As I mentioned earlier, we want to tackle pressure test record gaps. We want to tackle what I have always thought of as internal design pressure material requirements: wall thickness, grade, seam type. You know, the equation that you have in the design section of the code that says, here's what you can operate to. Some examples of what we mean, and these are all the things that are listed discretely out in the codes. And we intend on trying to address every one of them. Relevance to safety and integrity. We've heard some authors say, one size doesn't fit all on these on some of these record gaps. And whether they're relevant or not kind of depends on what records you do have and the quality of the critical ones. If I have a really good test pressure chart that has clear documentation associated with it, but it might not be signed by anyone, is that a real safety issue? Also, it's dependent on the quality and the quantity of supplemental records. Maybe I'm missing where the test stations were, but I have a watering plan, a dewatering plan, and a bunch of construction records that you can lay out in a story and say, this is how the pipeline got tested. We had a section start here and a section start here. It's probably pretty logical that would have been where the test station was. So supplemental records can build this story, and we want to see if there's an opportunity to lay down some standards or guidelines where you can use those. And a lot of this stuff is going to be highly dependent on the operator's history and operating scenario. Phil touched on this earlier. A lot of us have pipelines that run at low pressure, 150 class systems, where the pipe's good for 1,000, 2,000 pounds because it's small diameter. Some of this stuff has been in the ground and operating for 50, 70, in Enterprise's case, over 100 years. So we got to take that into consideration when we're going to say, we don't have a hydrostatic test record from 1924, we got to do something. These are important things to take into consideration. We've established 3 levels. We say there are things that are high relevance. These are things you absolutely got to have. You need to know the pipe diameter and the wall thickness. You need to know within some range what the test pressure was. We have a moderate relevance. These are things that are important, but we can make conservative assumptions about what they are. Pipe grade and seam type. If I don't know what my pipe grade is, I can always default to grade A, 24,000 pounds. The code gives us that option. If we don't know what the seam type is, we can always derate it down to a lower seam factor for lap weld until we can, verify that. Or maybe we don't need to because we don't need that kind of pressure. Low relevance. These are parameters that have no or very little impact on the pipe's ability to maintain MAOP. We recognize that these are things that are requirements in the regulations and you have to have, but they still don't have a relevance for MOP. Test media, test date, responsible party signature. Next step in our process is we're going to look at these parameters and say, okay, what integrity data can we substitute that we can analyze and look at and apply for that gap? And this needs to be done on a threat basis. If you have cracking on your pipeline, if you have long seam issues on your pipeline, then the data you're going to look at is going to be a little bit different than metal loss and mechanical damage as your only issue. So we acknowledge that we need to know the threats, we need to know the risks, we need to know as much as we can about the pipeline so we can look at the right data. And we primarily believe that ILI, for reasons that many have discussed today, is the primary data source. As Robert Hall indicated this morning, look for something that you don't know about. You know, ILI gives you that. But we are willing to look at other test data too. We think there's probably going to be some new or novel analysis techniques that may come out of this. Some things that we haven't been doing with the data but are still there. Or some things that maybe one operator is doing because they have a specific concern that are applicable across the board for this record gap or that record gap. A couple of processes we've identified so far that we think that are out there that can be used. As I mentioned, a lot of the standard integrity management processes, your threat analysis, fitness for purpose calculations, remaining life determination, repair strategy. Am I going to repair to MOP? Am I going to repair to internal design pressure? Am I going to repair to some fraction or multiplier of that? These are all basic integrity management concepts that we think can be leveraged. Liquid regulation has risk-based analysis. It's somewhat dated. I don't know how many operators are still actively doing that, but we think there's probably some procedures or analysis that operators have done in their RBA that may have applicability today with a reevaluation of it and, you know, how relevant is it today. A project that PRCI is working on is this concept of ILI equivalence to hydrostatic testing. This is really, we think, a big part of some of what these guidelines are going to be. And I'll go into that when we get into an example. Then we want to see if we can help further along how the in-situ materials testing can be used in a more global picture. And because we're just kind of getting started in this project, there's probably other things we're going to identify as we go too. I mentioned ILI equivalence to hydrostatic testing. Here's a brief schematic of what we mean, but it's essentially through fitness for purpose calculations for each threat you know about, you can come up with a set of defects that you have to repair up to the level of MOP, or some sort of safety factor above MOP if that's to make up for a gap that you have. And I'm not sure exactly where this PRCI project is, but I think they're close in being able to have something out there to look at. You know, some things that we'd obviously want to consider here is, you know, uncertainty in the ILI data, probability of detection, your statistics, what kind of sampling, all those other pieces that are part of integrity management that you do on your ILI data to be sure that you are making accurate decisions on what the tool's giving you. Process and technology gaps. We've seen a lot of things. There's a couple PRCI projects about the in-situ pipe testing. We heard Magellan talk about all the work they've done. I've also heard that there's some things out there that can get pipe chemistries in the fields too, in addition to yield strength. So it's another piece of the picture is getting filled in. But what we don't see, at least from the PRCI project standpoint, is we don't see the protocol that brings it all together. What are the validation requirements? How many samples do I need? And Steve talked about this earlier, and other presenters talked about it earlier. We recognize that gap too, and we're going to try to fill that gap. You know, how are we going to correlate that data with ILI data? You know, direct assessment hasn't proved to be what we hoped it would, but there's some concepts in direct assessment that I think about how you bucket all similar pipe together. You know, when you establish regions in the ECDA process, you say, oh, this pipe has similar characteristics, so we're going to apply this sampling on that pipe. This pipe has these type of similar characteristics, so we're going to apply this testing on that pipe. Some of those ideas we think might work here, to develop a protocol that says you're going to take your ILI data, you're going to look for different types of pipe, and you're going to sample each different type a certain amount. How much? Those things are things we need to work on. There's other important data out there that's going to be part of this too. You know, we have a very helpful document put out by ASME that documents the history of line pipe manufacturing in North America. We'd love for it to be updated. You know, we'd love for more contribution into that because it's somewhat dated. But there's very valuable data in there that we can use to understand whether the data we're using is real or not. You know, there's been lots of talk about 30-inch seamless pipe that PG&E thought they had. Well, if you look at that book, you'll see never made. We want operators to be able to look at their construction data and whatever operational data they have, and that may play a part in how we make this protocol. And then, as we have failures or we do one-off metallurgical tests, we want to pull that data in too. And finally, we're going to develop the guidelines. We have different applicability of integrity threats, different levels of relevancy for missing records, differences in quality and quantity of supplemental records are going to be, we've got to be flexible to account for these things. Right now, we're trying to decide whether a very, very complicated flow chart or series of flow charts is the way to go, or maybe we need a table. And as we start to assemble these pieces, we're trying to work through the actual vehicle for delivering these guidelines out. So that's kind of one of the things we're working on right now. And we're certain that we're going to identify certain scenarios where hydrostatic testing is the right way to go. And may even offer some guidance of how to conduct that test to make up for your gaps. We're not saying that we're going to be able to solve everything without testing, but we're going to try to identify where we can. So maybe an example to kind of bring this together, what we're thinking is, and this is, we have a situation where we have no calibration certificate for a hydrostatic test. We acknowledge this is a regulatory requirement. We have to have it. It was an old pre-regulation test. We don't have it. We think this is a low relevancy parameter because we can account for it. If we think worst case, if we don't have a calibrated test station, the test pressure that the pipe saw would be lower than what our gauge is telling us. That's the worst case. But can we make a conservative assumption about how far off that test equipment may be? Do we know what the expected deviation is, what's typical? What's the most likely worst case? Is the MOP on this particular pipeline governed by internal design, wall thickness, grade, rather than hydrostatic test pressure? Did they test it to 100% SMICE? So if the actual hydro pressure is 10 pounds off, it doesn't actually impact MOP at all because MOP is governed by 72% or the Barlow formula. We think this particular example is a good candidate for the ILI equivalency approach. We think there's error in our MOP. What changes do we need to make to our ILI data analysis to make up for that? Do we want to change our repair philosophy? Do we want to increase the repair pressure? Say this particular line, we're just repairing to 1.1 times MOP or 1.25 times MOP. Maybe we want to increase that a little bit because we think there's some error in that MOP number. Maybe we look at what tolerances we're using in the ILI data and add something there. We've identified kind of a process gap here. There's not a lot of information out there, at least that we knew about what's the typical error in a hydrostatic test station gauge chart. Is it 10 pounds, 50 pounds, is it 100 pounds? Not a lot of stuff out there. We're certain that we can go to certain groups like maybe NIST, and they can help us put some parameters around that. This is kind of an opportunity for PRCI to say, hey, we can do some work on this and get some guidelines out for the industry. And kind of to summarize this is kind of what our guideline might look like. Determine what your potential gauge error is. Compare this to your current MOP and how your MOP was established and what impact it might have on the validity of that number. Adjust your ILI response strategy to account for that. I want to thank Jerry Rao and Mark Piazza for helping out in this presentation and for really showing a lot of leadership on this project. That's all I have. Any questions? Thank you.
Thanks, Jake, and really thank you, all the operators. I was jotting a lot of notes down myself, and a lot of stuff kind of resonated with me, too. So, I heard from Carl and a few others, this chart, very complicated, but then I also heard we're doing a lot of this stuff anyway. So is there anything on this chart, and let's get into it a little bit, but there's stuff we all agree on, we can knock it out. What I kind of heard in this presentation, yeah, let's go to subpart E, so we have the box on subpart E, but then I heard some operators concerned about, well, I'm okay with that part, except I don't like the spike test. So is it really the spike test as part of that 9 that's the issue, or is it something else? And then when you go to subpart E, which I agree, I think Steve and I looked before this workshop, how many operators are really doing your risk-based alternative per 195.303 that's already been in the code for how long? We haven't had many, and maybe the reason why, it's either not working or it could be antiquated, but I guess I'd have questions to any of the operators on either one of those to start. So really, is it the issue of the pressure test or the spike test in number 9? Is there something else about subpart E that's not working for us right now? I think Richard Kuportz might like to have a comment, question.
Rick Kuprowitz, president of Accufax. I'm usually brought in to be an independent, neutral observation investigating pipeline failures, usually ruptures. Does anybody here in this room have an idea of what the operating stress level was for the Marshall, Michigan Line 6B Dilbert pipeline release? It's a matter of public record if you want to go chase it down. It was about 52% Smythe, well below MOP, even though they were operating at reduced operating pressure self-imposed by the operator. Does anybody have the idea of what the operating stress level was for the Mayflower failure in Arkansas a couple of years ago? The operating stress level at the time was about 52 or 53% Smythe. Both pipelines were operating Dilbert. Now, I would challenge, and it's good to hear the comments today. I think everybody's trying to get there someplace. We're talking about crack evaluation. And I guess the question I'd ask of the group is how can you do crack evaluation if you aren't evaluating fatigue analysis in terms of Smythe? Because all the experts that talk to me about this stuff is they usually quote Smythe ratios and do pressure cycles as a percent of Smythe. And so an observation for their group in the subpart E, when we go to references of subpart E, I think there are many conscientious operators who are trying to meet the intent of the regulations, but the regulations do not specify Smythe. They specify a hydrotest ratio. And the smart operators, even before all the federal regulations, if you go back to PG&E records and whatever, you're going to find hydrotests, minimum and maximum test pressures, both in PSIG and percent Smythe. That's nothing new, all right? What's missing in the regulation is the correlation to get to that Smythe. Now, if someone has a newer approach to go with this, I'm open to hear it. But when I hear operators doing a subpart E, the first thing we go check, how does that equate to the Smythe level? And where does the operator in his operation, you know, is he at 72% Smythe? Is he blowing past that? Or is he operating real low, all right? And in terms of pressure cycling, I'm trying to look at, here's a benchmark to your hydrotest or your subpart E determination, if you've done a hydrotest, and then start evaluating and have the mechanical fracture experts say, given pressure cycling spectrum, here's my predicted time to failure. And it's all tied to Smythe. So that's a long-winded way of getting to the point here. One of the weaknesses in the current regulations is there are pipeline operators complying with MOP determinations in liquid pipelines who are dropping hydrotest ratios, still getting, or excuse me, hydrotest pressures, still getting the 1.25, but they're passing a hydrotest MOP certification, but they're leaving damn long and damn deep cracks in their pipeline systems. They may or may not come back to haunt you, depending on what you're operating. And I was talking to someone earlier today about an issue related, and I want to just enter into the record here, because it wasn't addressed in the National Academy of Sciences study on Dilbert. You got a unique character on Dilbert, a hypersensitivity on viscosity to temperature, all right? And if you're operating your pipelines at a certain lower temperature range, you better be really paying attention to your pressure cycling spectrum. Because there's a new term I'd like to call hyper-aggressive instead of very aggressive. No, most pipelines, if they're operating at high horsepower input, are operating at warm temperatures. To do those evaluations, you've got to go to Smythe. So I'm going to challenge the industry to, you know, look, where can we improve the federal regulations? You can have the IVP flow charts, or you can say, you know, let's improve on reporting how we do an MOP test for hydrotesting. I've probably said enough today to get everybody's attention. Thank you.
Anyone care to respond to any of that, or, I guess, as part of this, a lot of good comments there. I guess I'd ask maybe Alan and Ken, since we're moving pretty far ahead, I know some folks want to go early flights if possible. Should we segue, just bring all the rest of the panelists up? Because some of these are good regulations questions and that, so I'm wondering if we could just go right into the panel discussion. Yeah, I guess any more questions from the operator, anything from the webcast? And I guess, again, I'd ask the operators, have you done the 195-303? Is there any experience with that? Has it worked, not worked, the risk-based alternative for older? Because, again, we tried to look through our data, a couple citation issues, things like that, but we've had trouble seeing how many are actually using that, or successfully or not, so we just don't know what the reason is. So, does anyone have experience with the 195-303 risk-based alternative, or? Any other questions? We have anything from Twitter, or at least for this panel? Jake also mentioned a history of line pipe. I know Mike's here. I'm on ASME too. I can't remember. Is that one of the projects that might go forward or not? History of line pipe, updating that? Do you remember that one at all? Well, you might need to hit a mic. Mike Rosenfeld's going to come up. There was a comment I think Jake had about the history of line pipe, maybe updating some of the ASME guidance there.
Mike Rosenfeld with Kiefner plus RTD. A couple of attempts have been made to propose revisions or updates to that document, both to account for changes in the pipe manufacturing industry and global procurement issues, correct some errors, possibly expand it to things like coatings or fittings. There are a number of things that could be done to enhance its usefulness. Right now, the issue is the intellectual property of that book belongs to ASME, excuse me, and currently they don't. They need to see a business case for funding that. There's not something that they've got the funds to support. So there has to be some sort of an approach has to be developed that acknowledges that IP with funding from somewhere, operators or some other part of the industry, and a path for executing that. So right now it's kind of stalled.
Well, thank you. That was helpful. Any other questions, comments for the operators? Alan and Ken, are we okay just segueing into the full panel?
Why don't we take a 15
You want us- Okay. Yeah, we'll take a 15-minute break, and then we'll have everyone come up for the full panel. Thanks, everyone.